Okay. Yeah. So, welcome again to this fourth week of the course, Nature and Properties of Materials, an introductory course. Um, I hope you have been watching the lectures and watching it carefully enough so that it would not be a problem solving the assignment. But anyway, I'm there to help you all. Uh, this is the fourth week, and I'll be solving some sample problems uh, that will be helpful for you for the assignment. And if you feel like asking questions in between, please do interrupt me. Or if you feel like writing it in the chat box, please do that also. Uh, Either way, if you have any problems or any queries or questions, please do ask. Okay, please feel free to ask. And whenever you encounter a problem, you can also write in the chat box also. So yeah, let me share my screen first. Here in the screen, share. Okay. So can you see my screen? Can you all see my screen now? Okay, okay, fine. That's good. So let us just move on to the questions. So this week's lecture, it's all about coordination number. It's all about solid solutions. It's about covalent bonding and covalent materials and ionic materials and all these sort of things. And you'll encounter voids. If you have seen the videos, you have encountered what are called voids, what are octahedral, tetrahedral voids, and how they're important for substitution. Let's say you are making a solution of two solids. How they are important. Will the impurity sit in the host atoms place, or will they sit in the voids? So that is what you learned about in these lectures, and the questions are also, sample questions are also based on those. So let us just first encounter the first question. So they've asked that the coordination number of an atom in an octahedral void, right? So to do this, let us first draw an octahedra. That would be the first things. First things first. So let us draw a simple cubic. So close packed structures. The first octahedral void for close packed structure, right? Closed packed structure. So yes. So closed packed structure, that would be your face-centered cubic, FCC, and also similarly your hexagonal closed packed structure. So if you draw face-centered cubic, so just draw face-centered cubic, right? So draw a cube, okay, right? Here, when you are talking about crystal structures, the drawings are very important. So you draw a cube. Now you place the atoms, right? So for face center, there will be atoms at the corners, and also there will be atoms at the faces, right? So this is your, okay, this is one, all the corners are shown. And also, just for simplicity, these are all the same atoms, but for distinction purposes, I am drawing it in different color, all the atoms at the faces, right? So on top, this face, this face, this face, and this face, right? So so this bluer corner atoms. All right, and these red ones are the atoms of the bases, right? So so what you all can do is that for octahedral voids you have to have this octahedral structure, right? So drawing with a different color what your octahedra would be. So these are all sitting on the center of the faces. This is on the top face and this is on the bottom face and these are on the sides. So let's just join it, right? So yeah, so if you join this, join this, join this, and now join each with the top ones, right? So this will be this. Now all those will be also joined to the bottom. So this is your octahedra, and simple enough. What you can see is that the octahedral side will be occupied by this atom, right? Okay, so they'll be touching each other, this atoms, they'll be touching each other. This interstitial sides means that you are putting an atom inside those sides, inside those empty spaces, without absolutely distorting the crystal structure. I mean, without distorting any other host atoms. So these are all host atoms, right? So these are all host atoms. So without distorting these host atoms, you are attempting to put an atom inside the empty space. So as you can notice about this, these are all regular tetrahedras. Why? Because they all are at the center. So what they will be, they will have, so from, if this is the origin, so this is half and this is half. So root under a by 2 squared plus a by 2 squared, and that is a squared over 2, and that is a by root 2, right? So they are all, these octahedra, they all have sides, or they all have sides of length a by root 2. So they are regular octahedra. So regular octahedra. All right. So now the question that is being asked is that the coordination number of an atom in an octahedral void is. So this pink atom, this is the octahedral void, and the atom sitting on that void. So the nearest neighbors, they're all at the same distance from each other. Like this pinkish atom, they are all at same distance from this reddish atoms, right? So the octahedra. So 1, 2, 3, 4, 5, and your 6. So there are 6 neighboring atoms. So automatically the coordination number of an atom in an octahedral void is 6, right? So the correct answer would be 6, right? So there are 6 nearest neighbor atoms on the octahedral void side. All right. So let me just check for questions. Please ask questions if you don't understand. Write in the chat box, or you can directly ask if you face any problem. And please take this as not as just knowing the answer. Please try to follow. These lectures are uploaded right away, so please try to follow what you are being explained, right? So this is not just you gulp up these answers and you just put it in the assignment and you get marks or whatever it is. So this is not the right way. But please try to understand the concept, watch the videos, and also try to understand it in class when you are, right? So the next question is, what kind of geometry is adopted? Let me just check if it's recording. Yes, it's recording, absolutely. What kind of geometry is adopted by the polyhedra formed by 4 sp3 hybrid orbitals, right? So if you look into it, sp3 hybridized orbitals, like let's say, take for example as already been shown in the video, methane, right? All right. So carbon atom and four hydrogen atoms bonding, and they are covalent bond sort of bonding, and they are sp3 hybridized orbitals, right? So carbon is 1s2, 2s2, and 2p2. All right. So for the second or energy level, the energy diagram would be like this, right? So S is completely filled, okay, and the p orbital, you have two spins only for carbon, right? So there are three more you can accommodate, right? Sorry, four more you can accommodate. So that will be taken care of by the hydrogen atom, which is 1s1. So four hydrogen atoms will contribute to, they'll share this their one atom electron, and that will do the job for the bonding. All right. So P, this is 2p, this is 2p, and this is 2s, and this is 2px, 2py, and 2pz. So how do they look like? This is S, this is S, and for the orbitals, this is like this. So this is X, Y, Z, right? So this is your X, Y, Z, and your if it's this is like this is 2px, px. I mean just for carbon I am drawing. So this is 2px, and this will be your this will be your 2py, 2py, and this will be your 2p. This is along the axial direction. All right. So you already learned about in plus 2 level. So this is not very new to you. And what is done is that if you have a carbon atom center, this is not what you have, right? So as you know that the bonding is not like 90 degree or so. So this is not the case. But what you have in hand is that they have the tetrahedral structure, right? So if this is carbon atom, so this is hydrogen at on top, this is one hydrogen on top, this is one hydrogen on top, and this is one hydrogen on this side, right? So they form a tetrahedral structure. Okay, somebody wants to join. Okay, okay. Now, yeah. So back to where we were. So this is so this is it. Right. So this is this. This is this, and this is this, right? Okay. So and this is right. Sorry. So for let me just draw it fresh. Okay. So this is carbon. This is one. This is one. Where the hydrogen. So this is the structure. So this is what you have, right? So these are all hydrogen atoms. 2, 3, and 4. This is a tetrahedral structure, and this bond angle this is approximately 109.5 degrees. So how do they bond? So they bond like this. So this is carbon. Okay. This is carbon. So these are the lobes. So these are the lobes. These are the lobes. One lobe is this. One lobe is that, and one lobe is this, right? So drawing is not very good. So pardon me. So let's draw it different color. So this is this. This is this. This is this. This is sort of. So and now there overlap of orbitals, and these are the hydrogen atoms, right? So this is direct overlap of atomic orbitals. So this is this. So this is this also. Complete overlap. So the carbon atom is at the center, and there's overlap of the orbitals between the carbon and the hydrogen. So for P and for P, and this is the axial. So for P and X, this is the thing, Px, Py, and Pz with the hydrogen atoms. So this is the overlap of atomic orbitals, right? So we assume the tetrahedral structure. So my point was just to explain that how do the bonding happens. You have already learned in the video, but just explaining it a bit further for you to understand what kind of geometry is adopted by the polyhedra formed by 4 sp3 hybrid orbitals. So for CH4 is a sp3 hybridized orbitals in the tetrahedral structure, as you have already. So the correct answer would be the tetrahedral structure adopted. All right. So the next question is the size of an interstitial atom that can fit into an octahedral void of a cubic close-packed structure formed by host atoms of radius r. Right. So that is one question, and what you're going to answer is that. So just think about this. Let me just draw it again. So this is your cubic structure, right? So this is your cube. This is your cube, right? So what you do, so the atoms, their corners, right? Draw different color, the face centers, atoms. Let us draw with this violet. So this is this, this is this, this, and this is this. All right. So we found out that this has to be connected. And this is the pattern that we get. This also. Now this is your octahedron. All right. So now this sits at the center. If had it been a body center, it would have sit at the center. So this is this. So this is the solid color. So this octahedral side void. So what you can understand is that although I'm drawing these spheres or this just as a point, small points, but they'll be like this. They'll be like this, and they'll touch each other, right? So what you have to see that the size of the octahedral atom. So size of the octahedral atom. Let us just denote by R oct, right? So you see that this is, if this is a sphere, you are not distorting anything, absolutely nothing. So you are, this is a sphere, this is the half of a sphere that touches the sphere that sits at the void, and also the sphere from this face also touches the sphere that sits at the void. So what you can basically see that this R from this, and 2R from this oct. So basically what you get is that this distance and this distance is your A, basically, because it's a simple cubic structure, and this if you have side A, right? Sorry. You have side A. Okay. So 2 of R is the radius of host atom. Radius of host atom. Alright. So 2R plus 2R oct is your A. But from your FCC rule, what you have is that you have 4R is equals to A. A is 2 root 2R. Simple. Just draw a diagonal along this. So this face cube that sits sphere that sits in the face touches these spheres also. So 1 of R, 2 of R, and that makes it 3 of R, and another R, that is 4 of R, and this face diagonal is root 2A, right? So this is basically the identity that you use. So A is root 2R. So let's just put it in here, and this is 2R plus 2R oct is equals to your 2 root 2R. So basically, these two cancels out, and R oct becomes root 2 minus 1 of R, and that is root 2, that you know is 1.414, and that will be 0.414R. So simply, your R oct will be the radius of the octahedral atom that is at the octahedral void. So R oct is 0.414 times the radius of the host atoms. So your correct answer would be 0.414 R. So smaller than the radius of the host atoms, right? Okay. So in the next question, in cubic closed packed unit cell, there are, the first option is 8 tetrahedral voids, each of which is shared by 4 adjacent unit cells. So tetrahedral voids, let's just draw your, sorry, let me just in between check if there are questions. If people have any question that you need to ask, please feel free to ask. I'll just wait for 1-2 minutes. If you don't have any question, then I can proceed. Okay, fine then. So I hope it's same with everybody. But please ask questions if you find that you are not able to understand. So it's a good practice that you ask at this point, because whenever exam comes or whatever it is, that just don't read in with exam in mind, but just read for knowledge. So that is this. So let's just move on to the next question. Okay. So tetrahedral voids. Let us just do it. So if I draw a face-centered cubic closed packed structure, so join. Yes. Okay. So now, if I draw again, I'm tired of drawing. Okay, but anyway. So these, this and this. All right. Now the face-centered atoms, I'll just draw with a different color, just to make sure that it's consistent. And see, now you have to have an octahedral void, right? So you can always take one host corner atom and the 3 face centered atoms. There are 4 2 atoms, so 4 atoms from the 3 atoms from the face centered. All right. So what you can do is you can always you can have this structure, right? So with the popping color, yes. So that is this. You have this, you have this, right? Yeah, you have this, you have this, and just you have this. So this is your tetrahedron. All right. So just okay, let me just draw it properly. Okay. So now this is this, and this is this, and you join this two, right? So this is your tetrahedron. All right. So and if it sits at the octahedral void, that sits at this your at this sorry. So that at this one, right? So as you can easily understand that this is your this is along the body diagonal, right? And if you see that there are four body diagonals, and you'll naturally have two along those two body diagonals, that is along uh, this part, along this, along this, along this, along this, along this, and along this, and along this. So if you have along one body diagonal 2, so there are four body diagonals, and you will have 8 octahedral tetrahedral voids. So within one unit cell, which contains two atoms, it is not a primitive unit cell, it contains two atoms. So the tetrahedral voids, there are 8 tetrahedral voids, and you get to know that this is the tetrahedral void. All right. So there are 8 tetrahedral voids within the unit cell, and why they are not shared by adjacent unit cells? Because they sit at the inside of the unit cell. All right. So that is this thing. So the answer would be your 8 tetrahedral voids within the unit cell. So yeah. The lattice parameter A of a metal with cubic close packed structure is 2.8 angstrom, the size of an impurity atom that can fit into the tetrahedral void without displacing the host atom. So what you all can do is just do this. I'll just draw another one. So this is this. Just for the sake of simplicity, I'll just draw another set for solving this problem. Okay. So take for this ones. This is for this. This is for this. This is for this. And this is for this. Okay. So now what you can do is you can also draw with these, like these, yeah, these. Okay, so you can always draw this as the tetrahedron. So along this body diagonal, this will be this. So the tetrahedral void will sit at this, which is, as you know, that this is the 1 by 4, 1 by 4, and 1 by 4 of A, right? So okay. So 1 by 4 and 1 by 4 and 1 by 4 of A. So basically what you see is that this is 1 by 4 of the body diagonal, right? So 1 by 4 of the body diagonal will automatically mean that your body diagonal is root 3, right? Root 3 of A. So the length of this would be root 3A by 4, right? Okay. So root 3A by 4 will bring on to OA. So if this is your so if this is your O, this is your A, so your OA is root 3A by 4. Now if this atom sits at the center, they'll touch each other, so this total distance will be root 3A by 4 will be R tetrahedra. This is assume that this is a sphere and it will touch this corner atom, right? So radius from this corner atom and one radius from this atom that sits at the void. So R tetrahedra is R of the host atom, right? And A is your A is 2 R. So root 3 by 4 into 2 root 2 R is R tetrahedra plus R of the host. So basically what you have is R is R plus R tetrahedra is your root 3 over root 2, right? So our tetrahedron is root 3 over root 2 minus 1, and that is 1.732 by 1.414 minus 1, and that will give you as 0.225 R. Right? So now the problem that is asked is that the lattice parameter, your A is 2.8 angstrom, so your R will be A by 2. Sorry, so let us just find R first. Your A by 2 root 2, right? So that is 2.8 by 2 root 2, and that comes out to be 2.8 divided by 2 root 2, that is 0.9 angstrom, so that, like that, right? And the size of an impurity atom that can fit in the tetrahedral wire without displacing the host atom. Of course, now you found out that it is our tetrahedra is 0.225 R. Just multiply with 0.225 and you'll get the 0.22 angstrom, right? So your R tetrahedra would be 0.225 times 0.99 angstrom, and that gives you 0.22 angstrom, right? The correct answer is a short numerical, but understanding is important. Just that you know it and you get to it. Okay. So, which of the following combination forms extended solid solution? So, you know, uh, from the lecture itself, this is directly from the lecture. So, from extended solid solution, there's a rule that is noc22 rules. So, you know that your copper zinc will not be, copper is FCC. So, your copper is FCC. Sorry, copper is FCC. Your zinc is HCP, right? They are also HCC. Okay, so nickel, silver, gold, they are all HCC, right? So there has to be same crystal structure. So I am not just quoting from the video itself, but you know that copper zinc will not be possible. Copper, silver, and gold will be possible, and your copper and nickel would be possible because they have comparable electronegativity, they have comparable structure. Those two combinations, they have comparable structures, and they also have comparable valence, right? So the right answer would be your, you have seen the video, it's copper, nickel, and silver and gold, right? So that was very simple, and that is directly from the video. And number 7, so possible locations of octahedral voids in body-centered cubic unit cell. Now you have been doing face-centered cubic unit cell, which is closed pack structure. Body-centered cubic unit cell is not a closed pack structure, but anyways you are asked. So what you'll do is you draw a body-centered cube. Okay, so this is your first simple cube, right? This is your first simple cubic structure, and this is your, yeah. Now the atoms sits there, right? And the central atom I draw it the different color. This is this, right? So the octahedra, if you have to take it, you have to take help of the adjacent unit cell also, because the atom that sits at the adjacent unit cell, at the center of the adjacent unit cell, will help in forming the octahedral structure. And what you do is simply you just join it and you'll get the octahedral structure, right? So this is your simple octahedra, and the octahedra void will be at the center of this top face, which is your this is your half 0. Now this is not the only possible scenario that this is the octahedral void. What you can also do is, uh, let me just draw a proper picture now. So let me just draw this adjacent. So also, yeah. So this is this. You have this. You have that. Okay. So you have this form, right? You have this form. Okay, and also you have along these directions also. Okay, and this directions also, right? So what you can think of is that if uh, if you are taking the uh, you know the atoms that sits at the uh, what should I call it, this body diagonals, sorry, let me draw with different color. So yeah, so I'm just drawing only the atoms that sit at the body center. Okay, what you can do is you can join these on, and this part also. All right, so the void will sit here, right? So it is on the edge, right? So coordinate is, so this coordinate is half 0 0, right? So the correct answers are half 0 and half 0 0. All right. So now the next question. So these are the two possibilities, right? You can have an octahedral void in this fashion also, an octahedral void in this fashion, right? So which of the following is not a Hume rotary rule for extended solubility in substitution and solid solution found by the elements A and B? Not remind you that this is asked, not a Hume rotary rule, right? So the first will be the structures and valences of the elements A and B would be different. It has to be similar, right? It has to be quite similar, quite close, right? So that is not the correct statement. So you have to take it. The size mismatch between the atoms of A and B should not be more than 15%. This is a correct statement. So this will not be the answer. The structure of the elements A and B should be similar. This is also correct. And the elements A and B should belong to the same group in the periodic table. Not necessary. It can also belong to the same row of the periodic table. And this is it, that the statement that the elements and A and B should belong to the same group in the periodic table is also not correct. So electronegativity has to be of the same order. So it is not necessary that it has to be along the same group. All right. So along the same column. So this also has to be ticked off. Right. It's also simple. The following is our examples of intermetallic compounds. These are directly from the video, so I'll not just go deeper into it. And the answer is cementite. Here, this is your Fe3C having fixed composition, and these are intermetallic compounds having fixed composition, right? So Fe3C is cementite, and this is basically iron and carbon composition here, and a certain composition of carbon in iron substitution will result in steel formation, right? So this is Fe3C cementite. So fixed number of three atoms of iron and one atom of carbon. So cementite is the following among the four options given. Is these are intermetallic compounds, right? So following these are attributes of intermetallic compounds. So first of all, they have, you know, long range ordering in crystal structure. They obey Home rotary rules because they don't obey Home rotary rules because they have a fixed composition, and depending on it, they will not necessarily have same valence or same of the same electronegative character. They'll not obey Hume-Rothery rules. Their compounds of fixed position, that is correct. And they have ductile nature, that is also not correct, because they are not flexible, they are very hard in nature, so they cannot be made into wires. So they do not have ductility, they do not have a ductile nature. So that is also not correct, right? Oh, let me just talking. Question number 5. Okay. Question number 5 is what? 5. Okay. So Venkatesh, do you have any problem with question number 5 still? Please, can you respond? Venkateshan, please, can you respond? And if you still have problems with question number 5? Anyway, I'm going to go over it again. So, so this is about the tetrahedral void, right? So tetrahedra, there is 1/4 of the body diagonal. If you draw this tetrahedral void sits at the 1/4 of the body diagonal, and another tetrahedral void will be at the 3/4 of the body diagonal. Just like from this, it is 1/4. From this origin, it will be 3/4, right? So 1/4 of the body diagonal will consist of this distance OA, right? So visually, what you can understand is that there is a sphere there, right? There is a sphere here also. Okay. So surrounding the center, you have one of the radius of the tetrahedra and also radius of the host atom. And as the distance of total OA makes a distance 3 root 3a by 4, that will be a combination of one radius from this host atom sphere and one radius from this void atom sphere. So R tetra plus R, and from from FCC consideration, this 4a is root, root 2R. Sorry, your 4R is root 2a. As I saw, as I showed you, that just consider this. This will be one radius of host atom, one radius of the host atom, that makes it 2, and one radius of the host atom, the 2 radius actually, this diameter considered, the 2 radius of the host atom, that makes it 4 radius of the host atom, and that is, this diagonal is root 2a. So from this you get it a root 2r, and the rest part is simple calculation. So the OA distance, that is 3a by 4, is composition of this radius and the void atom radius. So just proceeding on to get the answer, right? So I hope it's easier to you, Venkateshan. And let me just move on to the next questions. Yeah, molybdenum has a BCC crystal structure, an atomic radius of 0.136 nanometer, and an atomic weight of 95.94 gram per mole. The theoretical density of molybdenum is in gram per centimeter cube is. So the formula, formula what you have is rho is Na by Bc times Na. N is number of atoms per unit cell. Right? Okay. A is the atomic weight of the element concerned. Alright. Bc is the volume of unit cell. Right? And Na is your Avogadro's number. Right? So basically for BCC, for BCC, N is 2, right? 8 atoms at the corners, 1 by 8 shared by 8 cubes, so 1 by 8 times 8, 1, and add atom at the body center, so 2 atoms. Okay. A is given your 95.94 gram per mole. BC, which is actually the A cubed. A cube. But for BCC, you have to calculate this A cube because you are given in terms of atomic radius, right? For BCC, what you have to do is uh, for BCC is for BCC is so for a BCC structure 4R, like from previous lecture, 4R is root 3a. So the body diagonal, it will consist of 4 radius of the host atoms and the body diagonal is root 3a. So A is 4 by root 3R. So combining all this, and Na is 6.023 in 10 raised to 23. So the density would be 2 times 95.94 gram per mole, right? And this is your 4 by root 3, sorry, 4 by root 3 into 0.136, right? 4 by root 3 into 0.136 cube, because the volume of the cube is A cube, and this is 6.023 into 10 raised to 20. So I will not do it myself. So just keep in mind that this is given in nanometer, so you have to convert in centimeter cube, right? So keeping in mind that, you do this, right? You have to convert this nanometer cube into centimeter cube, all right? So rest will do the job. So this is fairly simple, and you'll be able to find the answer, right? So this is fairly simple. Let me just check. Problem. Yes. So when condition you are convinced that you understood the question number 5. Yeah. So 12 is also fairly simple. It's directly from the video itself. So which of the following materials does not crystallize in diamond cubic structure? And that would be your graphite. The silicon and zinc sulfide does, and that will be your graphite and magnesium oxide. Diamond cubic structure. Silicon has also a diamond cubic structure. Zinc sulfide, a zinc blend. This is your zinc blend structure, wood-side structure, and that will be also a diamond cubic structure. So graphite and magnesium oxide will not have this diamond cubic structure, right? So which of the following is or are true for diamond cubic structure? All right. So diamond cubic structure, just like I have a thing to show. So diamond cubic, basically it is FCC. Also these dark gray colored atoms is sit at the corners and also at the face centers, right? And also there are atoms at the tetrahedral voids. And as I said that these are families of 1 by 4, 1 by 4 and 1 by 4 atoms. So simply what you can do is which of the following is true for diamond cubic structure. This is basically an MCC lattice, and motif at 0, 0, 0, motif at 0, 0, 0 is this is at 0, 0, 0, and you have this as also not this is not 0, 0, 0. So by this diagram, this is 0, 0, 0. This is 0, 0, 0, and this is your 1 by 4, 1 by 4 and 1 by 4. The rest is simple. 0, 0, 0. If you point out the origin, you can draw an face center cubic structure, and also the tetrahedral voids, which is for the diamond cubic structure, sp3 hybridized. You can have this 1 by 4, 1 by 4 and 1 by 4 atom, right? So the correct answer for you is FCC lattice with motif at 0, 0, 0 and 1 by 4, 1 by 4 and 1 by 4. So the head-to-head overlapping of atomic orbitals results in the formation of your sigma bond. So earlier in the second question I about the sigma bond. So this is this head-to-head overlap of sp3 hybridized orbitals. They give you the sigma bond, right? And they are the strongest, right? Okay. So your sigma bonds head-to-head overlapping gives you the sigma. Okay, and the last question, which of the following crystals has the least atomic packing fraction? Body centered cubic also does not have. Face centered cubic absolutely does not have, but the diamond cubic structure, which I showed you, has the least packing fraction, right? So they'll not touch each other and there will be empty spaces. You can visualize, and this is a homework task for you all, that let's visualize with a clear head that such is the position of the diamond cubic structure, such that it has the least atomic fractions. So I'll just leave a question mark for you all to think about. Alright, so we finished question number 11. Question number 11 is what? Question number 11. Okay. No, Venkatesan, I'll not give you the answer because this is really simple. And please bear with me in understanding that I'll not give you the answer for that question, and that is for you to calculate. I've done everything except for that I have not calculated the numerical, right? So that will be for you people to calculate. And yeah, well, you just be able to answer it, right? Yeah. So density, it is given for you to understand is that Na by Bc into Na. So this N is number of atoms per unit cell, and A is the atomic weight. Bc is the volume of the unit cell, right? So let me just write. So this is your body center tube, right? Okay. Okay. So the atoms will be there, will be there, will be there, here, there, here, here, and also at the center. So what actually happens is that although I have drawn as smaller spheres, actually they'll be like this only. These spheres, and also these spheres, they'll be like this only. Right? So they'll be touching each other. So they'll be touching each other, and also this sphere will also touch. So this corner atoms and the central atom, they'll cover the body diagonal, right? So 4 of R, this is R, this is R, this is R, and this is also R, right? So 4 of R will consist the body diagonal. So in the problem, what's the most important thing is that it's given that it is the atomic radius that is given, all right? Atomic radius is given, that is 0.136 nanometers, right? So 0.136 A is R is your 0.136 nanometer. Okay, so now you have to find A as 4 by root 3 into R. Okay, just find A from this, and just simple. So rho is N, A is also given, BC and Na. BC is volume of this unit cell. This is your unit cell, that will be A cube. So A is given, right? Is given. So volume BC is 4 by root 3 A whole cube, right? Understood? Sorry, R. That is not A. That is R, right? So put it in place of BC, and Na is your 6.023 to 10 raised to is somewhat given, maybe is given. Just put it in that. This is for an exercise. I'll not do everything. So this is also for you to understand that I'll not do that feed. So understanding from it, you have to do this. Correct? Okay. 8th and 10th question. Okay, fine. 8th and 10th question. Okay. So, which of the following is not a Hume-Rotary rule for extended solubility in substitutional solid solution formed by the elements A and B, right? So, when you are mixing two solids, the Hume-Rotary rule, what it says is that Hume-Rotary rule says that the first point is the size difference between two atoms. Size difference between two atoms must be less than 15%, right? So the hello. Okay, so that is it. So size difference would be, has to be less than 15%, because you think that if the impurity site, if the impurity site atom is greater than the size of the host atoms, it will not be able to accommodate. So here you found out that uh, for a octahedral void, the atom has to be smaller than the host atom, right? It is 0.414 R, right? So assuming such structure, if it's an ordered structure, if you are going to put an impurity atom in this octahedral void site, it has to be smaller than the host atom. So it can't be much larger than host atoms. But in that scenario, you cannot have this interstitial site atom, right? So it will distort the atomic structure or the unit cell structure. All right. So the size mismatch between the atoms of A and B should not be more than 15%. That is correct. So that's why we are not taking it, right? The structures and valences of the atoms A and B could be different. That is not correct, because when you are having an ordered structure, let's say for copper and nickel, solution, they both are FCC, right? But for copper and zinc, that is copper is FCC and zinc is HCP. So there will be lattice mismatch. Okay. So there will be not a, so that will not be a good solution of solids, of two solids, right? And the valence, right? So copper, nickel. So valence, you would understand that for copper it is 1 and for nickel it is 2. So there has to be close, right? For to form the stoichiometric, like stoichiometry of the copper nickel solution. All right. So the structures and valences of the atoms A and B could be different. That is not correct, right? So that is why we dictate, and we are asked about what is not correct. The structures of the elements A and B should be similar, and that is also true. That has to be similar to have a good solution, right? The elements A and B should belong to the same group in the periodic table. It can belong to the same periodic table, because for extended solid solution you have an example silver and gold. They form in the same group in the periodic table. They can be, but it is not hard and fast that they have to be in the same group in the periodic table. Let's say copper and nickel, they are not in the same group in the periodic table. They can be in the same row from left part of the periodic table to the right part, but not very far away, because then in that case the electronegativity will differ. Like let's say for at the furthest left it will be electropositive elements, and at the furthest right there will be electronegative elements, right? So the electronegativity also has to be comparable. So it can't be far enough, but it can be in the same row, or cannot be in the same. So that's why we are taking the option that this is not correct. The elements A and B should belong to the same group in the periodic table. That is not a hard and fast rule. It can be, but it's not necessarily have to be. Okay. So that is why we are taking it, right? And 10. Following is or are attributes of intermetallic compounds. So they have long range ordering in crystal structure. So for solids, you have to have a fixed crystal structure. You cannot be brittle, right? So it has to have a certain type of ordering, and that has to be maintained at long distances. So intermetallic compounds, they're metals, right? The stoichiometry, of course, they're solid solutions. You're talking about alloys, but for order structure, they have to have this ordering maintained till long distances. So they have long range ordering in crystal structure. The first criteria of it being intermetallic compounds is that they're compounds of fixed composition, like cementite. They are Fe3C. So 3 atoms of iron and 1 atom of carbon, right? So they have to have fixed composition. And concerning this non-trivial option of that they obey Hume-Rotary rules. So these Hume-Rotary rules, they are putting on restrictions, right? So they are putting on the restrictions that they have to have same comparable valences, they have to have comparable electronegativity, they have to have similar structure. But for interstitial compounds or intermetallic compounds, they did not necessarily have to have the same structure. They absolutely can be, but in that case, they will not be extended solid solution if it's not a same structure or same sort of thing. So copper and zinc, all right, they do not have the same structure, but they are interstitial compounds, intermetallic compounds, right? The zinc, they sit at the interstitial sites and all these sort of things. So in that case, they do not necessarily have to follow the Hume-Daughtry rules, and that is why they are not the attributes of the intermetallic compounds, right? They do not have to have very comparable electronegativity. They can be comparable, so they'll be have in that case they'll have extended solid solution, right? But not necessarily they have to have this solution. I mean copper, zinc, right? So 35% copper, zinc dispersed in copper. The vice versa, 1% copper dispersed in zinc. In that case, they'll not have the same, they'll not maintain the same structure, the same valence of the two atoms. They'll not maintain it. So in that case, they not necessarily have to maintain the Hume attributes. Okay, so that is why I said these two answers. Okay, so Simran, do you have any further problems? Yeah. So anybody, please feel free to ask questions. I'm there to answer your questions. Please feel free to ask. Yeah. And these are recording. This recording of these sessions will be uploaded for your convenience. So it is a bit longer. So I'll just wait for 3-4 minutes. Please ask questions. If you don't have any questions, please go over the videos once again. Please go over this session once again so that you find it easy to answer the questions. And if you have any further questions regarding today's lecture, this week's lecture, I can also ask in the coming week when I will be coming for the 5th assignment, right? All right. I don't see people have question. So can I wrap up if you have no further question? It's already 1 hour. Anybody does not have nobody has any question? So I'll just wrap up here. Please go over the videos, understand fully. If you have a problem, please ask the questions in the next session. I'll be happy to answer your questions. Okay. Okay, then stop sharing. Just. Okay. Thank you.